This module will cover the Michel-Levy chart, what it is, how to read it, how to use it. And that uses a couple of new terms for you: retardation, which is noted by the symbol delta, and birefringence, which is the lowercase delta. And we'll use the Michel-Levy chart to estimate birefringence, and I'll show you how to use value of birefringence to compare to the actual interference color that you're seeing in your thin section. Okay, this is the Michel-Levy color chart, and you have a copy in your textbooks, and each of the optical mineralogy texts will have a nice copy of the Michel-Levy chart in them. You can also find them online. These are the interference colors that you see when you're using cross-polarized light. And so it's an interference color or birefringence. It's not actual color that you see in PPL. The birefringence, this interference color, can be quantified numerically using that lowercase delta, and the index of refraction, the high value of index of refraction minus the low value for the index of refraction for a given mineral. So how you read this is that value of lowercase delta for birefringence appears on the top part of the chart as well as on the right-hand side of the chart. Those are numbers that you will see listed in textbooks or those reference texts on optical mineralogy. You're never going to tell me what the birefringence of a mineral you're looking at in XPL down a microscope. You're never going to give me a number for that. You're only going to give me the interference color. Okay, the other parts of this chart are the thin section thickness on the left-hand axis. And you'll see that it goes from 0 to 50 microns. And the standard thin section thickness is 30 microns, so that's why this blue line is drawn across the color chart. That's typically what you're going to see. Now, you might have an instance where the thickness is slightly more or less in your thin section, and you would see a corresponding change in the interference colors that you're seeing. Typically, you can see that a thin section is the correct thickness if quartz is showing up to be have an interference color of a gray color. If it's slightly yellow or maybe even orange, that means your thin section is a little thicker than 30 microns, and that explains that. And then all the other minerals in that thin section are going to be correspondingly slightly different from what you would typically expect. The bottom part of this chart is the retardation, and you see values from 0 to 1800, and those are differences in wavelengths between the fast and the slow ray of the light that's passing through the anisotropic minerals. That's the word I was looking for, anisotropic. And you'll also see that it's shown first order interference colors here from 0 to 550, a second order set of interference colors from 550 to 1100, a third order, and on. So that corresponds to a repeating set of interference colors above. So first order goes from black or dark gray to these first order red, and then you'll see in the second order you move from violets, blues, greens, yellow, orange, reds in the second order, and then the same pattern with violets, blues, greens, yellow, orange, red in the third order. And you'll also notice that there's a different intensity to those colors, so that the first order colors look more dull, the second order colors are quite bright, and third order and beyond, so fourth order, etc., those interference colors look more pastel or washed out. How you read the Michel-Levy chart is, let's say you have, you're looking at a mineral in thin section that is second order blue, right where my pointer is. You can find out the corresponding value for the birefringence by moving along the radial line from second order blue up to following that radial line up to a value on the top axis. And that's going to correspond to a number. And that number is the number that you'll find in a reference text. So if you're looking at a mineral that is second order blue and that corresponds to a value of something like 0.02 in birefringence, then you're going to look in the text and say, maybe I think that's olivine. Look in the text, and is that an appropriate birefringence in the range for olivine? To see, is this right or not? Maybe it's not appropriate for olivine, and so it's not olivine, and you need to find an alternative. Or you could say, well, I think it's olivine. Look up this value. There's forsterite right there. So the magnesium end member of olivine has a birefringence of 0.033. That's the value there. To find out what kind of interference color that corresponds to, follow the radial line down to the appropriate thickness of 30 microns, and then look at what color retardation you should expect. And in this instance, for forsterite, you expect second order orange. So that's what this is simplifying for you. You have a value of birefringence on the top axis. You follow the radial lines down to the correct thickness, which is always 30 microns, or in this case it's listed in millimeters, so 0.03 millimeters, and that corresponds to a color. So this is the number that you see in reference text. This is the interference color that you see that corresponds to the retardation, and you will always aim for a thin section thickness of 30 microns. So what's happening with birefringence? In anisotropic minerals, the light is passing through the lower polarizer and passing through the thin section. The thin section, the mineral that's in the thin section, is splitting light into, for anisotropic minerals, into a fast ray and a slow ray. And the difference in the distance that light is traveling between the slow ray and the fast ray is the retardation. And those have values in nanometers that correspond to those interference colors that we were looking at. So, the frequency of the light remains unchanged when you split those, split the light into a slow ray and a fast ray. This frequency is related to the speed of the light divided by the wavelength. And the wavelength is related to the color that you're seeing. If the wavelength changes, the color also changes. Here's another way of looking at it. In just a cube of rock that is the thickness of a thin section, about 30 microns. The slow ray is traveling one distance. It's a shorter distance, and at the same time, the fast ray is traveling a longer distance. And the difference between those two is that retardation. And that gives us a particular value in nanometers that we read off of the retardation axis of that diagram. We can see this, and we'll try this in class, in a calcite experiment where you get double refraction. You may have seen optical calcite before. Here's an example right here, where you see the fast ray and the slow ray in a double image in the optical calcite. The light is split into two rays, and they propagate in and vibrate in different directions. Each is polarized, and they're perpendicular to one another. The ordinary ray, that's denoted by an omega, it travels straight through the crystal, and it vibrates in a plane that contains the c-axis, or the optic axis of the mineral. The c-axis is generally the long axis of the mineral. And the extraordinary ray, denoted by an epsilon, that's the ray that's deflected, and that is the slower ray of the two. And it vibrates in a plane that contains the other ray and the c-axis. Okay, so light waves could be in phase or out of phase when they exit the crystal. When they're out of phase, some component of the light gets through the upper polarizer and displays an interference color. And when one of the vibration directions is parallel to the lower polarizer, no light gets through the upper polarizer, and the grain is at extinction, or it looks black. So, to reiterate, at any given time when you're looking down the microscope, when the slow ray first exits the crystal, it's traveled a distance d. The fast ray has traveled a distance d plus the retardation. And because time equals distance divided by rate, you can calculate, go through this math if you like, but get to the point where the retardation is equal to the distance times the birefringence. And that distance is actually the thickness of the thin section, 30 microns. So, look at this again. There's the birefringence. Those are the values we see in the textbook. Here's the retardation, the difference in the distance that the slow ray and the fast ray travel. And there's the thickness of the thin section at 30 microns. You need to remember that when a common mistake is to look at the retardation, to look at the color, let's say first order red, to come up here and simply keep going straight and reading the value for birefringence off the axis. That's incorrect. What you need to do is find the color, look at a thickness of 30 microns, and then follow the radial line up to the axis for birefringence. That's the value that you need, and that's correct. Okay, so that color chart shows the relationship between the retardation, the crystal thickness, and the interference color. When we get first order red in that last example at 550 microns, and I showed you that those colors repeat, you'll see that at 1100 microns, at double that first retardation, you see the same reddish colors again. And it keeps repeating. So that first set of colors up to 550 microns is first order. From 550 to 1100 is second order. 1100 to 1650 is third order. And that the intensity of the color changes. Here's an example of quartz. There's the omega and the epsilon for the ordinary and the extraordinary rays. They have different values. You can calculate the birefringence of 0.009 for quartz. So for quartz, you're expecting a birefringence that corresponds to this value that's on your Michel-Levy chart. Any other orientation that's not parallel to the extraordinary or the ordinary ray, you'll get a lower birefringence color. When you rotate the stage, that color changes intensity, but the hue doesn't change. And you'll also see that every 90 degrees as you rotate the stage, the mineral will go extinct, and you also see at alternate 90 degrees, you'll see the maximum interference color at in between extinction directions at 45 degrees. So if you rotate the stage 360 degrees, you'll see 4 extinction positions exactly 90 degrees apart. Okay, so that value there is the maximum interference color for quartz. And the question is, when do you see that? And what color is that? And what interference color is that birefringence? So look at a Michel-Levy chart and see if you can find a first order gray color when you read the chart for 0.009 birefringence. Okay, so for estimating birefringence, what you want to do is find the crystal of interest, so one grain of the mineral that you're interested in, and you'll notice that they have similar optical properties, and so you can find a particular kind of grain that might be oriented optimally for this. You need to find a crystal that has the highest order colors, so the furthest to the right on the Michel-Levy chart. And that retardation depends on the orientation of the crystal. Then you go to the color chart, you find the thickness of 30 microns, use the 30 micron line plus the color, the interference color, and follow that radial line through the intersection to the margin and the upper margin and read the birefringence. Now, if you have a mineral that's second order green, what value for birefringence would you find in the reference text? Try this. What about a third order yellow? So go to the Michel-Levy chart, you can pause the video, and see if you can remember how to read the Michel-Levy chart appropriately, following that radial line. Now, there's a feature of crystals in thin section that we can exploit to help estimate which order birefringence we're looking at. And these are called isochronos. The crystal has a particular interference color, that birefringence, that is dependent on the thickness and the orientation of the crystal. So points of equal thickness will have the same color. But if you have, let's say, the edges of a crystal or parts of the middle of the crystal that maybe didn't polish the same, there's slightly different thicknesses, that's going to affect the birefringence that you see. And if we're looking at a crystal that has, let's say, thinner edges around it, you will see isochronos, or lines of equal color, surrounding that crystal. And where you have thinner edges, you're going to see that there's a lower order of color on the Michel-Levy chart. So a color that moves, that's to the left of the color that you see in the center of the crystal. You can look through that spectrum of colors in the Michel-Levy chart and count through the first order, second order, third order red to figure out which order color you're actually seeing in the center of the crystal. That should help. I'll show you another trick later to do this. Here's an image of what isochronos look like. So here's a mineral that looks like, well, it's sort of pale pastel red. We don't say pink. Red is the color. The pale characteristic, the pastel looking color, what tells us what order that interference color is. But if you look at the edges, you'll see there's a red. Then we go through the spectrum to another red, through the spectrum to another red, and then the colors change. What you're seeing are pastel colors on the top in third order, then bright colors in that spectrum in this next sequence of colors, and then they become more dull. You see the red, yellow, and then gray. What you're seeing is first order through to first order red, second order, and third order. So you're looking at third order red. You should be able to do this with other minerals. For instance, in the videos of thin section 1, you can test yourself. The centers of those crystals don't have a consistent interference color, but there are thinner parts when those grains were polished, and you can count through some of these isochronos and try to figure out what order interference you're looking at. So when you're describing and looking up the birefringence for a mineral, you want the highest order interference color, the furthest to the right, in order to describe that crystal. So that's the maximum interference color. That's third order red. And when you're describing birefringence, always use the interference color, describe that color, and the order of the retardation. So you might say second order blue, or in this case, third order red. You need both of those pieces of information to describe the birefringence. All right, what you learned in this is how to read and use the Michel-Levy chart, what birefringence and retardation are, that anisotropic minerals split light into fast and slow ray, and the difference between those rays is the retardation, that you can use isochronos to estimate the order of birefringence, and you can describe birefringence with an order and a color. For example, first order red, or you can use the shorthand with the degree symbol to say first order red for short. Now I'd like you to use the Michel Levy chart from your textbook or online and watch videos of thin sections 1, 76, and 100, then complete the quiz on birefringence.